Your chemistry diploma. Do we have to write what the date of the chemistry diploma is?
Might as well.
Might as well. Might as well. Hey, am I going to be able to do that? No, I'm not going to be able to do that. Okay, you have to write it down.
Oh, it's already down there.
It is, right?
Yeah.
Yeah, good. Okay, Tuesday, January 28th at 9 o'clock in the morning. Make sure you have breakfast that day. What are you allowed to bring into a diploma?
Nothing.
Your calculator.
Are you allowed to bring in food?
Yeah.
I think so.
In a clear bag, right? Something like that. So you can bring snacks. How long do you have to write the diploma?
6 hours.
Yeah, please, for the love of God, do not take 6 hours on your diploma. Now, the reason why I'm saying that, there's a perfectly good reason for certain people to take 6 hours writing their diploma. And they've been training for that because there's either a learning disability, or there's a very specific reason why they do that. And they're used to taking extra time. They're used to training themselves to taking extra time, okay? That time is not for the vast majority of people. And the reason why I'm cautioning you against it is because what kind of decisions do you think you're going to be making at 5 hours and 15 minutes into the exam? Very poor decisions. You're probably going to be changing answers that are right into wrong answers. Like, there's a higher probability of you doing that. There's only 60 questions. You should take an average of about 2.5 minutes per question. So that's like 2.5 hours. Okay? Now, are some questions going to be way quicker to answer than others? For example, the organic chemistry section. Can you probably rifle through a lot of those questions really quickly? Yeah, and then bank time for a lot of the other sections, right? In the really kind of heavy mathematical areas of equilibrium and stuff like that, you're probably going to want to spend more time there and a little bit less time on the organic section. Also, when we look at it, not each unit is weighted equally. Okay? Now, your program of studies suggests that we take 20% of our time in this semester to do energetics. They suggest we take 33% of our time to do redox. They suggest we spend 16-ish% of our time to do organic chemistry. And then they suggest that we take another 30% of our time to do equilibrium and acid base and stuff like that. Okay? So that's what percentage of questions will be on your exam related to this stuff. Okay? So if you were like desperately trying to pass the course, and you let's say you were equally as bad at every single unit, what would you focus more on? Equilibrium and redox. That's what I would focus on. And then I would give myself a stab at organic chemistry. You know what I mean? If you're just trying to pass the diploma, I just take a chance with organic chemistry, because you can probably figure out some of it, right? As long as you know a little bit of reactions, as long as you know a little bit of functional groups, stuff like that. Redox and equilibrium is where I would spend most of your time, because that's about 2/3 of the exam. What do you got to bring? You got to bring photo ID, right? I think you have to. They check your photo ID at the diploma. Pencil, eraser, calculator, extra batteries, sure, extra batteries. If you got to bring your cell phone or backpack, you got to leave it at the front. If your cell phone is activated and is it with you like during the test, you forfeit the exam. It doesn't matter. Like for those grade 11s who have never written a diploma before, if you have your cell phone on you and it goes off, no ifs, ands, or buts, you get 0 on the diploma. There's 0 arguing, there's 0 discussion, boom, 0 automatically. Good luck next time. Okay? So why? Does anybody know why that is? Cheating, because you could conceivably have a weird, crazy system set up where 2 buzzes is B and 3 buzzes is C. You know what I mean? Like there's an insane way of cheating, and so just don't have it on you. Put it in your backpack, put it at the front of the class, make sure it's turned off, blah, 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 blah. You guys already received the practice diplomas. You can go to Quest A Plus and select grade 12 chemistry, blah, 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 blah. here's like another version of these checklists. This is not totally inclusive. I want to be very clear. If your goal is to get 100% on the diploma, this will get you probably 97%. But there's probably going to be one question that's tested outside of these major concepts. I just want to let you know that if that's your goal, you can't just rely on this. What I want to do today is I want to do a very directed review of the equilibrium unit, but it's not going to be all-encompassing. It's not going to be everything. So this is just chapter 15, gas equilibria, and you're welcome.
Thank you.
I want to see how much you remember.
I do not remember anything from this.
Yeah, this is the very first chapter that we did. This was September 4th.
A time when I was happy. Right. I didn't want to stay in that. It's okay. I'm fine. Figure it out.
Just as a fun fact, this was approximately 3% of your life ago. Just as a fun fact. Yeah. Just whatever, it's all good, you know what I mean? Whatever.
3%.
Oh, we're
Yeah.
gonna be old. Shut up.
How did you even do that?
We're gonna be
5 months is approximately half a year, right? So, and I'm assuming that most of you are either 16 or 17. So when you go half a year, 0.5 divided by, let's just do 16, that's 3.1% of your life you've spent during Chem 30. It's just interesting, that's all, whatever, it doesn't matter. It's all good. Okay. When I look at this, equilibrium, an equilibrium is defined by you reach an equilibrium when the rates of the forward reaction and the reverse reaction are the same, are equal to each other, right? Because if you're in equilibrium, that means you're making something just as fast as you're breaking it back down into its original components. You're not gaining extra of this, and you're not gaining extra of that. You're just always going to be the same. So when I look at this, what are the two reactions that are represented by this equation here? It's a little bit small. I should have made it bigger, but whatever. What are the two reactions being expressed here? What's the forwards reaction? A plus 2B gives you 2C plus D. What's the reverse reaction?
G plus 2C.
Yeah, okay, good. Perfect. Okay. The Kc is 4.55. What does that tell you about this reaction? Yeah, it's the equilibrium constant, and the equilibrium constant represents the ratio of something over something.
Products over reactants.
Products over reactants.
Yeah, you did it.
So, because this, right, remember that's roughly equal to the concentrations of the products divided by the concentrations of the reactants. Is this number greater than 1, or is it less than 1? It's greater than 1. So what does that mean? Is our top larger, or is our bottom larger in the ratio? The top is. So is this products favored, or is it reactants favored? It's products favored, right? Howdy. Oh. Okay, thank you. Bye.
What's up, cowboy?
What?
Say what's up, cowboy?
Oh. Yeah, maybe I shouldn't say howdy in front of you guys. Whatever, that's fine. Okay, so let's draw a graph of like a typical equilibrium graph. On the side, we've got concentrations in moles per liter. On the bottom, we've got time. And what I'm going to do is I'm going to use the same color just because it's easier, but it's easiest. But I'm going to label it. We're going to start off with tons of reactants, and we're going to finish with, well, we'll see what we finish with. Okay. So let's start off with, this is A, and this is B. And then we're going to start off with C and D. Very little of C and D. So let's think about this. If we have products being favored over reactants, whose concentration should be higher? The products, right? C and D. So right now, at the beginning, are our products, are those concentrations larger? No, they're not, right? And that presents a problem for us. I'm trying to find the exams, and this is a huge problem for me right now. Oh, right here. Literally in the first place I looked. Yes. Yes, we can talk. On the next page, on the bottom half of that page, there are some equilibrium constants that I want you to try and represent. You're not calculating Kc, you're just writing the Kc expression.
Whoa.
I don't think it's doing this that good. So it's your
It's probably in the back.
Oh no, it's right here. Oh wait, what is homogeneous? So you're actually checking. It's homogeneous because it's on liquid. What'd you do this varnish? No, I'm not even a star here.
I think I did like good. Yeah, I walked through there like I might get 100. Like that's how it's spent.
That is 1 month away.
Like the questions and the practice stuff.
So I need to finish this book and I need to finish. I know. You're not on a roll, you're on a chair. I know, whatever. Oh. I tried to study and then my brain was like, go to bed.
Are you good?
No, I tried. I didn't sleep at all.
You're welcome. Got your stuff? Good. Okay. Okay. Okay, so let's get back at it. What's going to happen? Because this is products favored, what's going to happen to the concentration of our reactants?
It's gonna go down.
They're going to go down, right? What's going to happen to the concentration of our products?
It's gonna skyrocket.
It's going to go up, right? But how is it going to go down and how is it going to go up? Do you remember the shape that they take? It's a curved line. Is there a steep change at the beginning or at the end?
The beginning.
At the beginning. So they either go steeply up and then drop and then level off, or they go steeply down and then level off, right? Yeah. So A and B are both going to drop. A and B are both going to drop. And then they're going to level off. And C and D are both going to rise. So C and D are both going to rise. Hopefully that makes sense.
What? Wouldn't B be almost double?
B should have dropped by twice the amount.
Yeah.
I totally agree with you. I 100% concur. And I tried to show C was rising by double the amount. I'm just a crappy artist.
I was just making sure.
Yeah, I totally agree. That's a great question. Love it. Okay. So at what point in time on a graph can you spot when equilibrium has been reached on a graph?
Yeah.
Yeah, when?
When line goes straight.
There's no more movement in the line.
Yeah, when the concentrations stop changing, right? So on my graph, it's approximately here. That's when equilibrium has been reached. Now, there's a bunch of like visible or measurable properties that you could use in order to determine when equilibrium has been reached. Do you remember taking the solutions of the ethanol and the cobalt and stuff like that and heating them up and cooling them down? They either turn like more pink or more blue. Do you recall doing that? Yeah, so we can identify when equilibrium has been reached by when the color stops changing. That's not the only thing. That's not the only property that we can like see or measure and figure out that something has reached equilibrium. So when the color stops changing, something's reached equilibrium. What else? We can use when the temperature stops changing, right? And then kind of the last thing that we could use, it doesn't have to be the last thing, but when the pressure stops changing. Kind of the one property you can't use is mass. The one property you really can't use is mass. And why? Why is that?
So the mass is always going to be the same.
Mass is conserved during a chemical reaction, right? If I were to turn all of this into this, if I started with 30 grams of this stuff, how much do you know you're going to finish off with? 30 grams. So you can't use mass because mass will remain constant the entire time. So that can't be used, right? Reactions must be in a closed. Good. That's so good. This is not the only time we dealt with a system, right? In energy, we didn't want a closed system. We wanted an nope.
Closed circuit.
We wanted an isolated system, right? And so the reason why, and we'll talk about that in a second, we want a closed system. A closed system is where matter is not allowed to leave, but energy can. Have you ever heated up an equilibrium before to see what effect that had? Did you ever take one of those test tubes with the blue solutions and heat it up and cool it down? Well, that can't be an isolated system, because in an isolated system, energy is not allowed to leave or enter, right? So you heating it up and cooling it down would have had no effect. Can you understand what I'm talking about? Yeah. Okay, let's kind of draw why it's important to have an isolated system, a closed system. Jeez. Let's put a bin here, and my bin has a lid on it. Kind of looks like a pot on a stove or something. I don't know, whatever. So we've got a solution, and what's inside my solution? What's the thing that's dissolved in water? Ammonia. This is an ammonia solution. So we've got ammonia particles. Now, what is happening inside this? What's happening inside this equilibrium?
Becoming gas and water.
Yeah, so the aqueous ammonia, the ammonia that's dissolved in the water, it can escape and turn into a gas. I'm going to show that with an arrow leaving the solution. Some of these can leave, and after a little bit of time, am I going to have fewer particles in the water or more particles in the water of ammonia? I'm going to have fewer particles of ammonia in the water. So I'm going to draw 4. Whatever.
Why is that again? Because the energy is up.
Nope, it's because if some of these are leaving, Max, if I drew 2, 4, 6, 7, I drew 7 particles. If some of them are leaving, then we have to have fewer particles inside the water.
So it's like we're just slowing down.
Yeah, yeah. So then after a little bit of time, you'll have some particles in the air that are just evaporated out of the water. Now, would you agree the rate of ammonia leaving the solution is less now than it was a little while ago? Because there's fewer particles in the water. So the rate that's leaving is smaller, but what else is happening now?
The ammonia is turning back into the atmosphere.
The ammonia is going back into it as well. So as long as for every one particle that leaves the solution, one particle enters the solution, then we're at equilibrium, right? Are the same 4 particles, are the same 4 ammonia molecules always in the water at the same time? No. But when one leaves, one enters. So remember, that's not a static equilibrium, that's a dynamic equilibrium. We're still maintaining equal concentrations. Now, what's going to happen here if I turn this from a closed system into an open system? How could I do that?
Take off the lid.
Yeah, I could take off the lid. So now, when I open it up, what escapes our mixture now?
Ammonia gas.
The gaseous ammonia is allowed to leave. Do we still have ammonia particles leaving the solution? Yep. But what do we no longer have? Ammonia coming back in. So by opening up the system, are we at equilibrium? No, you've changed. You can no longer have equilibrium. Because as soon as one leaves, it's probably going to leave forever. Right? That's why we need a closed system. We need a closed system so that matter can't leave. Hopefully that makes sense. Okay, perfect. What would I do by increasing the temperature of the solution?
You'd be adding it.
I would be adding energy, right? And I'm increasing the rate of which reaction, the forwards or the reverse reaction? I'm increasing the rate of the forwards reaction. So what does that mean? If I heat this up, if I put this on a stove, right? What's going to happen? Am I going to get more particles leaving the water or more particles entering the water? More particles leaving, right? And that's the basis of Le Chatelier's principle, right? If I increase the energy, the system shifts to do the opposite of that. Okay, perfect. Equilibrium expressions. Homogeneous equations, do you remember this? We have to include every term, right? It doesn't matter if they're all liquid or all aqueous or all gas or whatever. So for example, in this one, what would be the Kc equal to? C to the power 4.
Oh, yeah.
Right?
Okay.
Oh, man, that is a blast from the past.
You dug into the depths of my memory.
Yeah, divided by what? A squared
Plus
b times b cubed, not plus, times b cubed, right? So it's the product of all of the products divided by the product of all the reactants. That sounds stupid. You're multiplying all the products, all the concentrations of the products divided by all the concentrations of the reactants. Good. So is this homogeneous or a heterogeneous reaction? It's homogeneous. Why? All the states of matter are identical to each other, right? They're all the same state of matter. Okay, perfect. I'm going to do this one over here because I'm going to lose out on some room. So Kc is NH3 squared over H2 cubed times N2. I really should be putting in gas here, but I guess my state of matter, whatever. Yeah, hopefully you're okay with that. And then the very last one, what's the Kc equal to? H2CO3 over CO2. And this is something that I don't know if you remember. Water, we ignore, right? But we don't really ignore it. What could we put there in place of it?
Hydrogen.
We just define it to have a concentration of 1. We just define it to have a concentration of 1. Because the problem is the concentration of water isn't going to change here. In an aqueous solution, do you agree the concentration of the amount of volume that the water takes up is really not changing by very much, right? So even if I add more of this or add more of that, like the water's not really changing its volume. So if it's not changing, then it doesn't matter what it is. And what's the simplest number to put in there? 1. And so we just define it to be 1. It's just easier on everybody. Okay, if at equilibrium the concentration of SO3 is this, the concentration of CO2 is this, the concentration of CS2 is that, blah, 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 then the Kc value, we're looking for the Kc. I would like you to go ahead and calculate that for me, please. Your answer should be close to 90.
87.7.
Yeah. Just a casual reminder, Kc, equilibrium constants, are always unitless, so you don't even have to put units inside your calculation, right? We just define them to be unitless. So
The temperature doesn't matter, right?
the temperature does matter, but the temperature doesn't matter for the calculation, right? We just have to, remember, we have to define the Kc at a specific temperature, because what's the only thing that can change the equilibrium constant?
Temper.
Oh, geez. One thing or two things? One thing.
Only one thing.
It's
Mass?
Nope. What is it?
Temperature.
Temperature.
Oh.
We have to define a Kc at a specific temperature, because if I change the temperature, I will change the Kc value.
Makes sense.
I like this example because it forces you to use some buttons you probably haven't used in a while.
Actually, a little bit. Not very much.
Yeah, unless you're in math or you
fresh water, something.
201, 0.90024. Oh shoot. It's so easy to forget a squared sign here. Super easy to forget a squared sign. So remember, our 0.9 is to the power 4, and our 0.289 is squared. Prove to yourself you know how to use your calculator to get a value of 87.7. And if you can't do that on your calculator, you need to stick around at lunch and we need to teach you how to use your calculator. Because it's high time you learn. Is that okay? Good. Hey, is this products favored or reactants favored?
Products favored. Yes.
Products favored because it's greater than 1.
Yeah. This is greater than 1. So is the top larger or is the bottom larger? The top is larger, and the top represents products all the time, right? So this is products favored. Good, lovely, awesome. As long as we're good with that. Okay, let's talk about Le Chatelier's principle. So I don't know if you remember, right? If I have a chemical reaction, let's say there's 3A gases plus 2B gases that give 4C gases. Do you know what I mean? What are all the things that I could do to shift this equilibrium? Hint, they're given on there, but what are all the things I could do? Change the temperature, change the pressure, change the concentration by adding something, right? Good, awesome. Okay, let's say plus 20 kilojoules, whatever. That doesn't matter to me. Let's think about this. If I add B, if I add more B to this container, which side is the equilibrium going to shift to? To the left or to the right? It's going to shift to the right. Yeah. So if I add B, right? If I add B, it's going to shift to the right. Because why? Why? Yeah, which reaction rate am I affecting by adding more B? Am I affecting the forwards reaction or the reverse reaction? The forwards. There's more forwards reaction now. And remember, we're not at equilibrium until both rates are the same. So if the top rate is way bigger than the bottom rate, then we're going to make more of this. We're going to make more of our products, right? Okay, if I cooled this down, if I cooled the solution down, would it shift to the left or to the right?
No. Go to the right.
Well,
Shift to the right so it makes more.
were you adding the energy? You're putting it down?
If I cooled it, yeah.
Shift to the right.
If I cooled this, Le Chatelier's principle says, whatever you do, I'm going to do the opposite of. So if you cooled it down, what is it going to do?
Heat it up.
It's going to heat it up. The only way it can heat it up is by shifting more towards that way. Good?
When you cool stuff down, the products are cooling down. When you warm stuff up, it's the reactants, right?
Depends.
Depends.
In this particular situation, yes.
On a question, will it be like, oh, the reactants are being heated here, or like?
No, because you can't heat reactants. Would you agree, all of these are all in the same container?
Yeah.
They're all sitting in the same container. So you don't heat up just the products or just the reactants. You heat up the container.
Yeah. So when you add energy to the container, does it go to the product side? Or the
Well,
reactant?
where is energy in our reaction?
The container.
No, but where is it in our chemical reaction? Is it on the product side or the reactant side?
It's on the.
It's on the product side.
Okay, that's
Because the reaction is releasing energy,
Okay.
right? So if we add energy, there's more energy for the system. We're increasing the rate of the reverse reaction, so the energy gets used up. It's not you're adding energy to one side or the other. It's you're adding energy, and it happens to be on this side, so you're increasing one of the two rates, right?
Into the kilojoules with my glasses.
Yeah, sorry, I'm just bad at writing, that's all. And then we can change the concentration by adding or removing something. Keep in mind, I'm not going to talk about it today. Okay, I'm not going to talk about it. But keep in mind, precipitation reactions and also acid-base interactions. But we're not going to talk about that today.
When are we going to talk about it?
I'm really not going to talk about it. If you find a problem as you're working through it, and you don't understand why that is, then you can come talk to me.
All
But
right.
I don't want to waste your time. I'm trying to get everybody to pass the diploma right now. So no, I think
He's ensuring.
I think the vast majority of us will. I really honestly do. Okay, but I'm trying to. Would you agree? There's no point covering a complicated topic if not everybody understands the fundamentals of that topic.
Yes.
Yes. Okay. Perfect. Okay.
Insurance policy.
Yeah. That's right. So what we're going to do, we've got this standard reaction, right? It's the formation of ammonia, and the delta H is negative 45.9 kilojoules. That's interesting. Now we're starting to combine units. Where is energy going to go? Is it going to be a product in our reaction or a reactant in our reaction? Is this reaction giving away energy or is it accepting energy?
It's giving away energy.
So this is plus energy. Would you agree? It's plus 45.9 kilojoules, but whatever, it's plus energy. So what we're going to do, if we start out like this, this is the way we're going to start out. So this is going to be N2, this is going to be H2, and down here is going to be NH3. I want you to show me what these changes will do at A, B, and C. And we're just going to say A's there, B's there, and C's there. I got to go answer a question. So I want you to graph these changes. And if you have no clue what's going on, then you can always move on to something else, and we can come back. By the way, it's okay if you have no clue what's going on, because again, it's been 3% of your life since we talked about this. So.
You.
Can give you another 30 seconds, and then we're going to cover this from the beginning to the end. Okay, that was 30 seconds. So it doesn't matter if you're done. Doesn't matter if you're whatever. I want you to look at your graph and then compare it to my graph. And it's okay if they're like a little bit different, but I'll point out the key things you need, right? Now remember also, does your diploma have any written on it at all? No. So you're not going to be drawing, but you're going to be analyzing things. So when I add N2, what's the first immediate thing that happens? You see how many spikes? One. You see one spike. N2 spikes up. Now, because I've added N2, what's going to happen? It's going to shift to the right. What does that mean? Shifting to the right. What the hell does that mean? We're going to create more products, and at the same time, we're going to lose both of these reactants. So your products should go slowly up, and both of your reactants should go slowly down. So your products should go slowly up and then level off, and both of your reactants should go slowly down.
Yeah.
Perfect. Now, we're going to increase temperature. I want to be very clear. I'm going to draw something, and you don't have to draw it at all. Here's a box, and it's got two things in it. Sorry, it's got 3 particles in it, okay? When I heat up this box and its contents, do the particles on average, do they get closer to each other?
Yeah.
They get
No.
like what I want to know is what's that this is that's stupid. I should have just done this. Okay, what if every red dot represents 1 mole, and this is in a 1 liter container? How many moles in this 1 liter?
3.
So this is 3 moles per liter. Now I'm going to heat it up. What does heating it up do to these particles?
Speed it up.
Oh man, meow, 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 right? They're just cruising all over. They're smashing into each other. What's happened? This particle hits and it just bashes into the wall. But what's the concentration of this hotter mixture?
3 moles per liter.
So did the concentration change?
No.
So are we going to see any spikes in concentration?
No.
No.
Whoa.
We will not.
Oh, you just did me dirty.
We will see no spikes in concentration. But what we will see,
Oh.
there will be no spikes. Nothing goes up, nothing goes down immediately.
Okay.
But slowly does something go up and slowly does something go down. Yeah, absolutely. Kelton, are you done or do you have a question?
Like, it's one that I don't really know, so might be done, might have a question, who knows.
Okay, well, I'm going to leave it in your very capable hands
But I'm
to
not
either
that
ask
capable.
me a question or to either hand in a test.
Okay, I'll ask the question when you're done.
Okay, great answer. Now, when we increase the temperature, are we adding energy or taking it away? We're adding energy. So energy goes up. So which way is this going to shift?
To the left, to the left.
So it goes up here, so it's going to shift to the left. Now, what the hell does that mean, shifting to the left?
You gotta cool it down, you know. So. You gotta go.
So we're going to use up the extra energy we added, but at the same time, we're not just using up the extra energy we added. What are we also using up?
NH3.
NH3. When we shift to the left, both of these things slowly go up, and anything on this side slowly goes down, right? So NH3 is slowly going to go down, and these things are going to slowly rise. And then the last thing, when I have a change in volume, does that change in volume affect everything or nothing?
I think everything.
Everything. Yeah.
Which one? Just add it all up. Right?
Yeah.
So which one's more? What do you take first? Beginning of the night.
Yeah. Right, so, okay, so what, so, yeah, I know. But what are your 2 reactants here?
What's the...
And whatever the heck.
I want you to do cocaine.
2 carbons.
Whoa. Okay.
And they're gonna react. One gets cold. gets pulled out every time, right? Every time you have an esterification reaction. So just draw that. How'd it go? Yeah, it was okay. Good. Here, I'm going to give this to you, but I also have something else to give you a little bit later. Okay. Yeah. Okay. Hey, are we increasing the volume or are we decreasing the volume? We're increasing the volume. So let's take a look at this. So the box is getting bigger. So instead of it being 1 liter, now let's say it's 2 liters. So now it's this big, right? That's terrible. So now it's this big. So now what's the concentration? Now these things can move around, right? Yeah. So they're getting more spread out.
Yes.
So is that more concentrated or less concentrated? Okay, so what happened to the concentrations of everything? Did they all go up or did they all go down?
They all go down.
They all went down, right? And what's the trick that we were doing with this to see which side it shifts to?
That's a good one.
The moles one.
Do you remember?
Yeah.
This goes down, right?
Yeah.
But how many arrows am I going to draw?
3.
Oh, I don't remember that.
And this goes down as well, right? How many arrows?
1.
This goes down. How many arrows? So on which side is there a greater change? So it's like this, right? So if there was a decrease on one side, then is it going to shift to the left or to the right?
To the left.
If I decrease this, what does the reaction want to do?
It's gonna
It's going to want to compensate and make more of it. So all of them go down, all spike down, okay? Wham, wham, wham. They all spike down. But which ones are going to go up and which ones are going to go down now?
So then the reactants are gonna go up.
The reactants go up. They slowly go up, right?
Why is this so?
And this slowly goes down. I'm starting to run out of room,
I
so.
don't have any
But that's not your fault, right? If I were creating, if I put more thought into this, would I have increased the volume or decreased the volume? If I were putting more thought into this, I would have decreased the volume. Whatever that's fine.
Because I mean we had 2 steps down, you know.
Yeah, I know. It should have been up, down, up for the one at the bottom, but whatever, it doesn't matter. Okay, so but does that make sense?
Yeah.
Okay. I want you to take 20 seconds and ask yourself the very last question on this slide.
Oh.
No, not the last slide, but the last question on this slide. What effect? Did the Kc go up when we increased temperature? Did the Kc go down, or did the Kc stay the same?
The only thing that can affect Kc
Because it changed temperature. So we know it affected it. It had to affect it. We just don't know if the Kc went up or down.
increase the temperature, wouldn't we be increasing Kc?
Okay, let's look at what, in general, what is a Kc?
Product over reactant.
In general, it's the equilibrium constant, but Kc is products over reactants. Now, take a look. What happened to the top and what happened to the bottom when we increased the temperature?
So the reactants went up and the products
So the
went down.
top lower than
So
the
it's
bottom.
reactants.
Yeah, this went down and this went up, right? So did our Kc get bigger or did it get smaller? It got smaller. So our Kc, it sounds stupid when I say Kc got smaller. Do you know what I mean? There's got to be a better English way of saying that. Kc decreased. Thank you.
This is going on YouTube.
Let me just say, you have the privilege of being taught by one of the smartest people in the world right now.
Oh,
Yeah,
that's a
Whoa.
Yeah. That's obviously a joke because I don't know how to English.
I'm too English.
Okay, so the Kc decreased. Do we all agree with that?
Yes.
Yeah, okay, good. Awesome. Good talk. So now what I want to do is I want to talk about ice tables. We're not going to do the most complicated. Oh, thanks. Yeah, no problem. We're not going to do the most complicated type of ice table problem that we possibly could, only because I just want to talk about this, and then I want to give you a little bit of time to do your own review if you want to. Okay? You guys okay? Yeah. Yeah, looks like it. Ice tables keep track of quantities or concentrations of chemicals during equilibria. What does ICE stand for?
Initial change.
Initial change equilibrium. And I need you to understand, 2 seconds, I need you to understand that when we set up an ice table, right? If I set up an ice table, and I have A plus B gives me C, whatever. We need to understand that the two sides of our reaction do opposite things. Would you agree? If we're getting a decrease on one side, what has to happen to the other side? It has to increase. It has to. You just can't argue your way around it, right? Also, I want to say is that each of these columns is like a little mini equation. Whatever you start with, let's say you started with 3 and you changed by -1, what would your equilibrium be? You started with 3 and you changed by -1. So what do you have at the end? Don't look at him, look at me. You started with 3. Yeah, that's right.
Okay, we went to that.
Yeah, please
That's
don't.
okay.
Yeah, please don't say that. Okay, you started with 3 and you changed by -1. So what is your equilibrium? 2, right?
Oh,
Yeah. You start with 3.
3.
Nobody saw that. You start with 3. You change by -1, and what are you left with? Boom. Every single column has to be a complete equation. It has to make sense in your mind, right? So if we start at 0 and we increase by 1, we have 1. Okay, that's really all we want to focus on. I want you to try to set up your ice table properly. Don't start solving it, but just set up your ice table properly.
I meant cool, Walton. I meant cool.
Are you saying that
You're already
is one?
No. I'm just saying, if you lost an x, if you started with 3 and you lost an x, then you would be left with 2. Yeah, but if you knew what x was, right, Preston? If you knew what x was, if you knew x was 1,
Yeah.
then you'd be able to figure it out.
I'm pretty sure it's
So when you gave me the test, you didn't give me a scantron,
Oh,
so I did it all in the book.
I meant cool, Walton.
okay. You're setting up the ice table, right? You're just setting up an ice table. That's all you're doing.
Because each term has its own thing. Okay, yeah, we're chilling. CS2 got.
Don't solve it, but like put in all the information you know for certain, and then we will solve it. And if you want to start solving, okay. So if you want to start doing extra reviews, I know it is correct. I'm happy with that. If you want to start doing extra reviews, okay. So are you just gonna hang it on your phone then?
No, just listen to you talk. Relax, it's me.
What the?
Whoa, I can't breathe.
So I'm going to fill it in. So initially, at a temperature 90 degrees, which you can't do anything with that, right? 0.18 mole per liter CS2. Okay, 0.18 mole per liter CS2 and 0.31 mole per liter H2. That's all they give us. That's the only stuff that they give us. Oh, sorry. I'm going to shut up for a second and I'm going to listen to you. They give us CS2 0.13. Good. Awesome. Now there are so many ways that you could solve this, okay? I think Shelby was saying that Zukowski, the way he sets this up, is he sets it up using almost like a molar ratio kind of thing, right? I like to figure this out by just using an equation, but maybe we'll try both. So what I want to know, because there's a lot of blank stuff in here, I'm just going to put in minus, why do I know this is going to be minus? Because we're starting with none of this, right?
I mean, plus it goes down.
Yeah, it goes down. So, okay, good. Minus what? What should I put minus here?
0.
So I could put 0.05, or I could put minus x, right? And I could say that x, 1x in this case, is equal to 0.05, right? So, okay, how much am I going to lose under hydrogen?
4x.
I'm going to lose 4 x's, right? But what is 4 x's? What's this times 4?
0.2.
0.20, right? Does that make sense? So the way Zukowski does this is he sets up some type of a molar ratio, and he says, I'm going to take this change, and I'm going to multiply it by that coefficient and divide it by the coefficient of whatever the change was. Okay? So it's this times the molar ratio of our unknown divided by our given. Does that make sense? It's the coefficient of our unknown divided by our given. Okay? So this times 4 divided by 1 is negative 0.20. Perfect. I got no problems with that. We're good to go. What is the change going to be for the methane? It's going to be plus for sure, right? Yep. And because the coefficients are the same, do you think they're going to have the same change? Yeah, perfect. So this times 1 divided by 1, so it's just 0.05. And then what's the change going to be under H2S? Plus 0.10. Good. So now we just add them up. Remember, initial plus or minus the change has to be equal to our equilibrium. So if I start with 0.31 and I lose 0.2, how much am I left with? 0.11. 0.05, 0.10. Now, there's so many things that we could do right now. I could ask you to calculate the Kc for this, and that would be totally fine. But what was the question really asking? What's the concentration of hydrogen gas at equilibrium, right? So what is the concentration of hydrogen gas at equilibrium? Hydrogen gas at equilibrium is 0.11 mole per liter. Are we okay with that? Yeah. Okay. So here's the deal. You have 10 minutes left. I'm not going to force you to do any one particular thing. Have I given you enough review resources, or it's perfectly okay to say yes or no, or do you need more review resources? Are we okay with that? If you ever need more review resources, please come talk to me and I'll get you more review resources. Okay, I'll get you more diploma questions and stuff like that. I'll get you more whatever.
Mr. Watson, why is it so cold outside?
Well, it's so cold outside because I believe it's a polar vortex. Now, I'm going to show